Well, hello, honors geometry students, and welcome back. I miss you guys, and I hope you're having an okay time, at least, learning geometry online. Remember, if you are having any difficulty at all, please, please, please email, call, do whatever you need to do. Get a hold of your teacher. It's all on eCampus and how to contact teachers. So please, please don't forget to get a hold of your teacher. Okay, well, we are about to start going round and round because this week we are going to start in on our circles chapter. In our circles, we go round and round. So this is chapter 12. The whole chapter is a chapter on circles. And I think that you'll find it's kind of fun because it's got a lot of stuff that we've already known, and then it does have vocab and stuff that we need to learn, but obviously a lot of application from things that we've done. So kind of puzzles, I like that. Okay, so let's go ahead and get started. Chapter 12 on circles. And now we look at 12.1. 12.1 is lines that intersect circles. Okay, so obviously we have a circle. First thing I want to remind you is if you have a circle, you name the circle by its center point. So this circle would just be circle O. So remember the symbol for a circle, and then it's just its center point. Also remember the center is not part of the circle, so it's only this part on the outside, like the circumference of the circle. That's the circle. Okay, so I have a couple of questions for you there. Where could the line be, and how many points of intersection could you have? So could I have a line that didn't intersect the circle at all? Well, obviously I could do that. I could come right in here, or even right through the center. It wouldn't intersect the circle, or I could have it out here. But since we're looking at lines that intersect the circle, we're going to erase that and say, well, that's not any fun. That's not anything we want to do. So instead, let's take a look at a line that would intersect the circle. So now if I put a line out here and say, here is my line. Okay, now my question is, how many points of intersection would that line have? Yeah, some of you are saying 1. Well, that might be true. There is point A, but remember from quarter 1, lines go on and on forever. So if I go on and on forever, it would have 2 points of intersection. So this line is called a secant. Now I'll give you a summary of all the vocab at the end, so don't worry about writing it all down right now. Just kind of think about what could happen. So a secant could intersect the circle at 2 points, or would have to intersect the circle at 2 points. So line A, what did I call it? A, B, we'll call it. That's a B up there, is a secant, line AB. Now notice it could have even gone right through the center. It really wouldn't matter because that's not a point on the circle. So is there any way of making 3 points on the circle? No, because even if I went right through the center, it would still just connect 2 points. So all my secants, and there'd be an infinite number of secants, could cut through the circle at 2 points. Is there a way, we know that the 0, that's not really intersecting, we know 2, is there a way we could have 3 points? No, because a line has to be straight. So the most we could have is 2. So then the question is, could we have 1 point? How could I just have 1 point of intersection? Let's say just that point. So what would I do to, you guys are so good at this, exactly. It's just like the tires on a road. If you're sitting your car out on the road, it's gonna have, the road is like the line, and that's gonna be tangent. So all those wheels are actually tangent to the parking lot. So we're looking at that point is the only point that it touches. And again, I'd have an infinite number. I could have a line going through A, I could have one over here, I could have one over here. So this is called a tangent line. This point is called the point of tangency. This is a secant line. And then don't forget the other lines that you've already had. We've had, for example, the radius. So we could put a radius in. So if I say I have a radius, we've had a diameter. I could put the diameter in. The diameter contains the center and 2 points. The diameter, assume I drew a straight line there, the diameter is actually called another segment as well. It is called a chord. And a chord, let's use a different color here, is any segment where 2 endpoints are on the circle. So I could consider the diameter to be the chord. In fact, there are some textbooks that would define diameter as the longest chord in the circle. But a chord is always just any segment that starts and stops, or it has its endpoints on the circle. So we'll call it segment XY. That would be a chord. So you could also define a secant as any line that contains a chord, because segment AB would be a chord, line AB would be a secant. I could not do that with this. There would not be a chord in this, okay? So those are just our basic vocabulary words here in 12.1. And we have two that are facts that I really need to look at here. And well, let's look at this first fact before I put it up there. Okay, it's talking about a point of tangency to the radius. So if I drew in a radius, we drew it in over there, but what if I drew it in right to that point of tangency? So I have this tangent line and I have this radius. When you look at that, it's always going to make a right angle. So if I come out here and I had this tangent line that I drew in, or excuse me, this radius I drew in before, if I drew in this tangent line, you see how it is? If I go with the end of the diameter, let's use this end, remember that was the diameter even though I kind of went crooked on it. Draw in that tangent, okay? So our first fact, okay, you can kind of see without any issues, would simply be a radius must be perpendicular to the tangent line at the point of tangency. A radius must be perpendicular to the tangent line at the point of tangency. And I do want to make sure you get that in your notes. We also have what we call internally tangent circles. So those would be two circles that touch the same point, but one's inside the other. And this one would be externally tangent circles. Again, two touching, and those would be, again, tangent because they touch one point. Okay, if you needed to find the equation of the line, I wanted to remind you, if I said I needed to find the equation of this tangent line, then I would find the equation of the two radii that are connecting here. Okay, so let's say that was like x equals 2. Okay, then I would also need to look at the horizontal line. Remember, vertical lines have x equals equations. Horizontal lines have y equal equations. So it's really going to be easy. This would be y equals 0. Okay? Here, I would just look at what point did that go through for my radius here, whatever point that is. So let's say it's 5. Then this would be an x equals tangent because it's vertical. So remember, vertical lines are x equal. Horizontal lines are y equal. And our second fact in 12.1, two tangent segments from the same exterior point are blank. Now, take a look first of all at what do I mean by tangent segments. Okay, so we talked about a tangent as being a line. Tangent segments then have to be part of the tangent line. So if I have a circle and I say, okay, I want a tangent segment from one exterior point, then I'm going to come out here, one exterior point, and I'm going to end up with two tangent segments. They're part of tangent lines, if I went on and on and on, but it starts at the exterior point and it stops on the point of tangency. Now, I said, what are those two tangent segments? So let's just label them. Here's A, here's B, here's C. Let's think about what we already know. So I'm going to look at what could I tell you about A, B, and segment AC. That's really what this is asking. Two tangent segments, AB and AC. What are they? You can probably guess at it from just looking. But if I think about the center of the circle and I draw in the radius, what do I know about that radius and that tangent? You're exactly right. It has to be perpendicular. This radius and this tangent, same thing. So let's say this is circle O. OB and OC would have to be what? Exactly, radii in the same circle, so that would make them congruent. Now that's another one that you'll see a lot, even though we've had it before. Radii in one circle or congruent circles are congruent. Then what would we know about OA and OA? Yeah, you guys got that down. OA is congruent to OA by the reflexive property. So therefore, I would have two congruent triangles, and I would know then that the two triangles are congruent by hypotenuse leg. Now, go back to our question. What do I know about AB and AC? You've just proven what we can now say. Those obviously are congruent. So that's a theorem, obviously, because we can prove it. Two tangent segments from one exterior point are always congruent. So let's take a look at how is that going to look on our homework. Now remember, I'm going to be doing guided practice problems from the reteach. So I want you to take notes from the YouTube video, and then you can put them right in your notebook if you want, notes from the reteach. Okay, so we're looking at saying, okay, in this problem, these two are tangent segments, so they have to be congruent. And this problem, in this circle, these two are tangent segments, so they would have to be congruent. Okay, and that was 8y minus something, a 2. Kind of got erased as I flipped it. Okay? Okay, so you guys are already saying, oh, well, that's going to be easy. So that's going to be, like I said, this is not that bad of work here. You just say, whoops, 8y minus 2 equals 36 minus 2y. So then I just add 2y to both sides. So 10y equals, add 36, or add 2 to both sides, so 36 plus 2, 38. So I would get y to equal, what? 3.8, exactly. Now, is that my answer? If it said to find AB? No, obviously not. I'd have to plug it in. So you can plug it in this equation, you can plug it into this equation, it wouldn't matter, and you'll get AB to equal 28.4. Okay, you get it? So it's not too bad. Look for those perpendiculars for the tangents and the radius, and look for my external tangents to be the exact same tangent segments. Okay? Let's move on to 12.2. Oh, yeah, well, that is true. I have a new little friend. I had to bring out the chick this week because it's my birthday coming up, and I used to get baby chicks when I lived on the farm every year for my birthday. Isn't he cute? So he's reminding me that we didn't answer the question for last week. Okay, the question was, why didn't the math student share her answer? Why didn't the math student share her answer? Maybe I need to write it. She was... Get it? She was too squared. Poor girl, she was too squared, or poor guy. I thought that was good. How about this one for this week, okay? I'm pushing on a balloon. What do you call the force when I'm pushing on the surface of that balloon? What do you call that force when I'm pushing on the surface of the balloon? Think about it. Email me the answers. You guys are doing great. And let's move on to 12.2. So 12.2 is going to be just an interesting part of looking at more vocab. So 12.1 and 12.2, we are looking at a lot of vocab. So again, I'm going to summarize the vocab with a sheet here in just a little bit that you can take a picture of. So now we're looking at arcs and chords. So in 12.2, it's just arcs and chords. Remember that chords are just the segment that has endpoints on the circle. So only chord in this picture then would be segment DB or segment BD. Okay? So that would be my only chord. Of course, AC would be a radius, and of course, a DB would be the longest chord called the diameter. Now we move on to arcs. Arcs are just parts of the circle, and there are going to be 3 kinds of arcs. Those that make exactly half the circle, that's called a semicircle. And again, I've got a whole thing on that you can copy down in a little bit. If I have a smaller than a semicircle, like this arc I labeled right here, arc BC, then arc BC would be a minor arc. Remember, that's like you're a minor because you're under 18, so minor arcs are under 180 degrees. Okay, so if I give you this arc is 80 degrees, it would be a minor arc. And a major arc would be everything above 180. So if I went from here all the way over here, that would be 180 plus the 80. Okay, that would be a major arc. Okay, you name every arc by either 2 letters or 3 letters. So that's what I wanted to show you on this, is looking at when are we going to use what. If I just say, what's the measure of arc DC? You have to figure out, am I saying from here all the way here, or am I figuring from here to here? Anytime it just has 2 letters, it must be the shortest distance. So it has to be this. So that's asking what's the measure of this arc? Well, you got it. If this is 80, this would have to be 100 degrees. DEB then is how I would make a semicircle. D to E to B. I could also name that arc BED just as easily, but every semicircle is 180 degrees. And then if I said arc DBC, remember that's that major arc. I have to start and stop on these first and last letters. So I got to start on D, stop on C, and then I have to go through B. Remember, an arc has to be on the circle, so no cheating across on the diameter. It's got to be the degree of all of this. So it'd be 180 plus 80, or 260 degrees. Okay, then we get into the new part here in 12.2, the central angle. The central angle is any angle whose vertex, guess what, is at the center. So if I had a central angle here, BAC would be a central angle. I could also say central angle DAC. So it has to have the center of the circle as its vertex. And the sides have to contain 2 radii. So if I wanted to look at that then, I have 2 facts in 12.2 that are very important. And that is that if I have a central angle, it's equal to its minor arc. So if this one is 80, this has to be 80 degrees. If this was 100, this would have to be 100 degrees. So our fact, a central angle equals its minor arc. Okay? And then really from there, we're just looking down at this one. There's going to be some other facts. I'll put them up here in just a minute. But all radii of one circle are congruent. So really what you're looking for are congruent triangles. So we had a fact here that says congruent central angles have congruent chords. I'll take a look at that. But really all I'm looking at here is saying, hey, look, these are all radii, so they're congruent. So wouldn't those 2 triangles be congruent? Doesn't it just make sense that BC would be congruent to DE? So central angle equals its arc, okay? And if these are congruent, then these chords are congruent. Let's try an example. Here's what we're looking at now. We're looking for those congruent triangles. So remember, anytime you put in, let's change colors here. Anytime you put in a radius, it's going to make, in the same circle, it's going to make the same. So that's going to be this. And look what they gave us. It says, if AB is 16, find X. Well, if I know that the radius is 10, then wouldn't every radius have to be 10? And look, aren't we looking at 2 congruent triangles? Now remember, I didn't say that this AB bisected. AB is a chord. It didn't bisect it. It just simply said, I want this little piece, and I don't know this piece. Okay, but I do know the whole radius. Keep that in mind. So now take a look at it. If these 2 triangles are congruent, so if that triangle is congruent to that triangle, and AB is 16, then wouldn't each of these have to be 8? And now you see you have a right triangle. I could say 8 squared plus b squared equals 10 squared, or I could use a 6, 8, 10 and say this piece is 6. Does that make sense? So I told you, it's kind of like little puzzles. I love this, okay? So if this is 6, is that my answer? Well, remember, every radius is 10. So if the radius is equal to 10, all I have to do is 10 minus the 6, and my answer would be 4. Now, we do have 3 theorems that you can write down from that looks at those 3 or those congruent triangles. So there's your 12.2 theorems. We had the first one already. If you have the same circle or congruent circles, congruent central angles have congruent chords. So you don't have to go through the triangles every time. You can just say, okay, they're congruent central angles, the chords have to be congruent. So some of the homework is going to go really, really quickly. Congruent chords have congruent arcs. Okay, again, if you go through the triangles, it's real easy to see, and therefore we'd have the central angle, and remember the central angle is equal to the arc. Okay, so we could prove that, but we're not going to take time to. And congruent arcs have congruent central angles. So again, if you have the arc, it has to be congruent to its central angle, and so therefore I'd end up with 2 congruent triangles. So it all goes back to congruent triangles. So really not too bad. So we're just going to end today by saying you can stop this, but I want to make sure that you get the vocab in for 12.1 and 12.2. That's the biggest problem here. So we're looking at a secant as a line that contains a chord. So secant would be line CD. So remember your notation on that. So a secant would be the line notation. You could also say line EB would be a secant. Okay? For the chord, it's a segment with endpoints on the circle. So BC, the diameter, is the longest chord, or EB would be a chord. So I gave you that example. Okay, and the circle itself is just named by its center. So circle A. Remember, to be congruent circles, they have to have the same radius. The tangent is a line that contains only one point on the circle. So this would be my tangent line. So line BH or line HB. Point of tangency is the point where the tangent line touches. Okay, so that would be my point of tangency would be point B. Congruent circles, I said, have to have equal radii. Oh, I didn't mention concentric circles because I think we saw that before, but concentric circles just have to be like a bullseye. So if I put a circle in here that has the same center but different radii, or a circle on the outside, okay, I can make numerous concentric circles. That's what concentric means. And then our other big vocabulary words, central angle, the vertex is on the center and its radius, or its sides contain two radii. So angle CB, nope, that's wrong. I made a mistake on that. A central angle would be angle DAB. I'm going to make that right here, angle DAB. That's in next week's lesson that we get into that kind of angle. So angle DAB or BAD. You could also say angle CAD or DAC would be a central angle. Okay, and then our last three vocabulary words, minor arc, an arc that's less than 180 degrees, two letters. So I could say arc EB, and that would be a minor arc. That's working with this part of the circle. It's equal to this angle. A major arc is greater than 180 degrees. I use three letters, so example there, arc CBE, starts at C, goes through B, and ends at E. Again, greater than 180 degrees. So it must be three letters if it has a major arc. It must be three letters if it's a semicircle. CDB, I know it's going to end up with C and B because those are my diameters, but I have to know whether I'm going this direction, CDB, or this direction, CAB. Okay? So you can stop the video and take a picture of that and put that in your notes. And then remember, you're also going to go through and have your guided practice. So you can put those right in your notes if you'd rather. I just want to give you a lot of examples since I can't be there in person. Okay? I hope to be able to see you soon. Thank you for your attention. Have a great week. Bye.